This is the homework helper for Chapter 8, Section 10 in the 8th grade workbook entitled Scaling Three-Dimensional Figures. Alright, so we're back to Chapter 8 after we've detoured back to proportions and ratios, and here we are now finishing up finally the geometry that we started a long time ago. So in number 1, 2, and 3, those use the same prompts, so we're going to go through those. 4, 5, and 6 are similar. They use a different prompt, so you're going to use the approaches you see in 1, 2, and 3 to help you solve 4, 5, and 6. Alright, so the prompt here for 1, 2, and 3 says that a 10-inch cube is built from small cubes, each 2 inches on a side. And we're supposed to compare the following values, which is something we would do in ratio form. And the first one is asking me to compare the side lengths of the two cubes. So the small cube is 2 by 2 by 2. The large cube is 10 by 10 by 10. So the ratio that compares the side lengths is going to be 2 to 10. And that's comparing the small to the big. Now obviously that is a reducible fraction. That can be reduced pretty easily. We can reduce that down to 1/5. Or if you want to write it in decimal form, that would be the same as 0.2. For every 1 in the small cube, there's 5 on the big cube in terms of inches. So the whole point here is they really want you to figure out, is the same ratio going to apply when we look at these other things? Is the same ratio going to apply when we look at the surface area and the volume in 2 and 3? Okay. So number 2 is asking me to find the surface area of the two cubes. Now as you can see, the formula you need there is on the upper right corner of the presentation, 2b plus ph, 2 times the area of the base plus the perimeter of that same base times the height. Well, the base here on each of these is a square, and the sides are the same. In the big guy, it's all 10s around, and in the small guy, it's 2s all the way around. So when we're talking about the little guy, the base there is going to be 2 by 2 or 4. So 2 times 4. 2 is just part of the formula. Plus that perimeter of that same base, so what you get when you add up the 4 sides of that base. So 2 plus 2 plus 2 plus 2, which is going to go together to make 8, times the height of that prism there, which is also the same number, 2. So we've got 8, 2 times 4 being 8, and 8 times 2 making 16, 8 and 16 making 24 for the small guy. Alright, when we go to make the big guy here, 10s now instead for all the sides. So the area of the base there is going to be 10 times 10 or 100, so that's 2 times 100. Perimeter of the base is going to be 10 plus 10 plus 10 plus 10, all 10s all the way around, so 40, times the height of the prism there, which is also 10. So 2 times 100 is 200, 40 and 10 there makes 400, so 200 plus 400 is going to go together to make 600. So when we're asked to compare the values here, the comparison is 24 to 600. But as you can see, and if we think about reducing that to try and make it the same thing as number 1, 24 over 600 does not reduce down to make 1 over 5. I can make the top 1 no problem by dividing by 24. But when I take 600 and divide by 24 in the denominator, the result is 25. So it's actually now, instead of being just 5 times as big, it's 25 times as big as the small guy, because the new fraction here is 1 over 25 when reduced. All right, let's take a look at number 3, the volumes of the two cubes. So length times width times height here. Well, this one's kind of nice because in the small cube, those numbers are all 2. In the big cube, those numbers are all 10s. So for the small cube, I just have to do 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. And in the big cube, I have to do 10 times 10 times 10. Well, 10 times 10 is 100, times 10 again is 1,000. So we're comparing 8 over 1,000 here. obviously that's not going to reduce down to 1/5 like we saw in number 1, but we can make the top number go to 1 by dividing by 8. So to divide the denominator by 8, that's going to give me 125. So this is 1 over 125. So now what you should be looking for when you're looking at 4, 5, and 6, see if the same thing happens here. When we looked at the side lengths of the cubes, it was 1 over 5. And then when we got to the surface area, it was 1 over 25. So this bottom number multiplied by 5. And then when we got to the volume, it was 125. So this multiplied by 5 again. You want to see if that same type of relationship exists in 4, 5, and 6. Maybe it does, maybe it doesn't. But the only way to find out is to actually go through and do the computations.